Professor Nathanson, I don't think there's sound on.
Okay. Can you hear me now?
Yeah.
Okay. So I'll start now for the third time. So a differential equation is an equation where the unknown is some function. We can call it u or f or y, whatever we choose to call it. And the equation involves this unknown function u and its derivatives. If you use a function of just one variable, we have what is called an ordinary differential equation, or an ODE. And if u is a function of two or more variables, then we have a partial differential equation, or a PDE. For example, if we have the equation, this is an ordinary differential equation, y prime equals 2y, that means find an equation, find the function y, whose derivative is equal to 2 times itself. And we saw yesterday, or we saw on Wednesday, and we'll see again today, that there's one solution of this equation, namely the function f of x equals some constant c times e to the 2x for any c. So this differential equation, this ordinary differential equation, has infinitely many solutions, because c can be any number at all, but there's really just this one parameter solution. You have, so from the point of view of linear algebra, we would say the solutions of this differential equation are one-dimensional. What's an example of a PDE? Well, we have what is sometimes called Laplace's equation. Sometimes you use this upside down delta squared u. This means it's the second partial derivative of u with respect to x plus the second partial derivative of u with respect to y equals 0. That's the equation. So this is the equation. Find a function u where of two variables, x and y, where the partial of u with respect to x, second partial, plus the second partial of u with respect to y is equal to 0. So, for example, if you are a physics major, as a couple of students in this class are, then you've probably seen this equation many times. How do we solve that equation? Well, that's not a trivial problem. What are some solutions? Well, suppose we let u of xy equal 2x plus 3y. Then the partial of u with respect to x is 2. So the second partial of u with respect to x, you differentiate a constant, you get 0. And the partial of u with respect to y is 3. And the second derivative is the derivative of the constant 3 is 0. So we get partial squared u plus second partial u plus second partial y is 0 plus 0 is 0. So that's a solution. That's one solution. What's another solution? Well, suppose we let u of xy equal, I don't know, e to the x sine y. If you differentiate with respect to x, you get e to the x sine y. And if you differentiate again with respect to x, you get e to the x sine y. If you take this function, you differentiate with respect to y, you get e to the x cosine y. And if you differentiate again with respect to y, you get minus e to the x sine y. So the second partial of u with respect to x plus the second partial of y of u with respect to y It's this plus this. E to the x sine y minus e to the x sine y is 0. So that's another solution. Any questions about this so far? I mean, you do have to know calculus. Suppose we let u of x, y equals the log of x squared plus y squared. If you differentiate u with respect to x, when you differentiate this with respect to x, you get 1 over x squared plus y squared times the derivative of x squared, which is 2x. And if you differentiate again with respect to x, when you differentiate this with respect to x, let's see, what do you get? By the quotient rule, you get x squared plus y squared squared. The derivative of the numerator, which is 2, times the denominator minus the numerator times the derivative of the denominator. So we have 2x squared minus 2x squared is minus 2x squared plus 2y squared over x squared plus y squared squared. So if you differentiate u with respect to x 2 times, this is what you get. And there's a symmetry here. If you differentiate u with respect to y 2 times, you should get minus 2y squared plus 2x squared over x squared plus y squared squared. So second partial of u with respect to x plus second partial of u with respect to y, when you add this and this, minus 2x squared plus y squared over this denominator plus minus 2y squared plus 2x squared over the same denominator, you get 0 again. So for this equation, the Laplace's equation or the wave equation in 2 dimensions, we get 3 extremely different solutions. This is a polynomial in x and y, a linear polynomial. This involves an exponential and a trig function. This involves a logarithm. So this is a very nice example because it indicates something of the richness, or if you like, the complexity of partial differential equations. This very simple looking equation has a multiplicity of solutions. And from the point of view of linear algebra, this is much more than a one-dimensional family of solutions. Okay. Now, when we look at partial differential equations, we saw there was a way to classify them. In fact, there are several classifications. One was the order of the equation, which is the highest degree that occurs in the equation. There's the number of variables. And what we're going to look at a lot are the first classifications of partial differential equations. These are second order linear PDEs. So second order means the highest derivative is the highest partial derivative, or mixed partial derivative is a second partial. Linear means, and it's in 2 variables, x and y. Sometimes we'll use x and t, but and we'll go back and forth between them. So if it's second order linear in x and y, if the unknown function is u, some function of x and y. We have u sub x, which means the partial of u with respect to x, u sub y, which is the partial of u with respect to y. These are the first partial derivatives. The second partials, there are three of them. uxx, which is the second partial of u with respect to y. uxy, which is the mixed partial of u with respect to x and with respect to y. And uyy, which is the second partial of u with respect to y. So if you're going to have a second order partial differential equation for a function in two variables, you have the function, you have the two first derivatives, and you have the three second derivatives. And to call the equation linear means you can have each of these multiplied by some function of x and y, but there's no product of a function u and any of its derivatives. There's no u squared or ux times uy. So we're going to have, if it's linear, it's going to be some function a is not necessarily a constant, times the second partial of u, plus b times the mixed partial, plus c times the second partial of u with respect to y, plus the two first partials, plus f times u equals some function. So a, b, c, d, e, f, and g are functions of x and y. Possibly, but not necessarily constants. Constant function is a very good function. So the general form of a second order linear partial differential equation in two variables looks like this. And there's a classification of these which are related to a kind of a quadratic equation. That I'm going to write down. But again, before I go on, let me ask, are there any questions about what we've done so far?
Hello?
Yeah.
Yeah, I just have a small question. So you were saying that it doesn't necessarily have to be a constant for it to be linear. Can you give an example of it being like a function?
Yeah. Let them all equal x or y or whatever, right? I mean, you could have x uxx plus cosine xy times uxy plus e to the y, sine x uxx. Right? I mean, so in that case, this is A, this is B, this is C, and so forth. Right?
And what were you saying when you meant that we should watch out that there shouldn't be like an x squared or something?
Oh, so linear means, so a nonlinear equation, you might have u sub xx equals u squared, or plus u squared equals 0. Because here we have u times u. So this is quadratic in u, or uxx plus partial of u with respect to x times the partial of u with respect to y, plus cosine xy equals e to the x. I mean, that's an example. This is nonlinear because, oops, sorry, maybe times u. Because here I have a product of two of these partial derivatives of u. So this is a nonlinear equation, or ux equals the sine of u plus 1, right? Because this involves the sine of u. In a linear equation, and PDE is linear, if you can have any of the partial derivatives of u that you like, but they all occur all sort of by themselves, multiplied by some function of x and y, but not related to u in any way. This is, so any equation, any differential equation you can write in this form is a second order linear PDE in two variables. And every second, and this is the definition if you like, every second PDE is second order and linear if it's of this form. Some of the A, B, C's and so forth can be 0, but it's of that form.
Can you repeat about the linear and nonlinear classification?
Yeah. If an equation looks like this, it's linear. If it doesn't, it's not linear. This is the definition, this red box. You have an unknown function u, and its derivatives is partial derivatives because this is a function of more than one variable, and it looks like that. Okay. Now, linear second order PDEs, this type of an equation, fall into three categories, which are called parabolic, elliptic, and hyperbolic. And they are directly related to what the graph of a quadratic equation in x and y looks like. You know, if you have a quadratic, if you have a polynomial in x and y of degree 2, the graph is a parabola, an ellipse, or a hyperbola. Or in a degenerate case, it might be two parallel lines. We'll see that in a second. So let me explain that classification. Yeah, is there a question?
Yes, this equation in the red box is one-dimensional or two-dimensional?
Has no dimension.
Oh, it's no. So
We're not talking about dimension at all. So I'm not associating any dimension to this equation. Certainly not now.
thank you.
So from this equation, I'm going to write an associated quadratic equation. The quadratic equation in two variables is ax squared plus bxy plus cy squared plus dx plus ey plus f. I'm going to make it homogeneous. That means the right-hand side is 0. So here's a quadratic equation. And if you graph it, that means if you look at all the points in the plane that satisfy that equation, you will typically get an ellipse, a parabola, or a hyperbola. And what determines which of these conic sections you get from this? So you have to know high school algebra. What we're going to do is complete the square. So I did this on Wednesday, but I'm going to do it again because this is basic high school algebra that you need to know for calculus. So you multiply by a, and now I want to complete the square. So this is ax squared. abxy is like ax times by. To complete the square, what do? You would add by over 2 squared. But if you add it, you have to subtract it plus everything else. So this is the same equation. I just added 0, this minus this. But the point, of course, is that now these three terms, this is ax plus by over 2 squared. What do I have over here? I can factor out a y squared. In fact, I can factor out a y squared over 4, and I have b squared minus 4ac. Right? This is b squared over 4. This is ac, which is the same as 4ac over 4. That's these two terms, plus adx plus aey plus af equals 0. So let me introduce some new variables. Let me introduce, suppose we let u be equal to ax plus by over 2. So then this is u squared. Minus b squared minus 4ac times y squared over 4. That's y over 2 squared. Plus ad times x. Let's see, x, from this equation, if I solve this equation for x is equal to u minus by over 2 divided by a. Let me just make sure I assume a is different from 0. Okay. So here I have adx. X is the same as 1 over a, u minus by over 2, plus aey plus af equals 0. Let's see, so I hope I did this little bit of algebra correctly. Suppose I let v be y over 2, just to make things a little bit easier, y over 2. So then this equation is u squared minus b squared minus 4ac v squared. If I did this correctly, the a's cancel. I have plus du minus bd times y over 2, bdv, plus aey, that's 2aey over 2, or v, plus af equals 0. So this is u squared plus du minus b squared minus 4ac v squared. And here, if I factor out a v, I get bd minus 2ae times v plus af equals 0. And I can complete the square again. If I add d squared over 4, I'll add d squared over 4 to both sides. So I get u plus d over 2 squared minus b squared minus 4ac. Here I just factor that out. I get v squared minus something. Well, If b squared minus 4ac is not 0, I can factor it out. And I'll get v plus some other stuff. I don't really care too much what it is. Let me just call it v plus, I don't know, k squared equals something, L. Yeah. So what is the consequence of this? Suppose I let u be u plus d over 2 and v be v plus k. I have an equation that looks like u squared minus b squared minus 4ac v squared equals something. This is b squared minus 4ac is not 0. And if b squared minus 4ac is equal to something, I have some equation that looks like u squared minus something times v equals something. Now, if this b squared minus 4ac is 0, this is a parabola. What is this? If b squared minus 4ac is positive, the equation u squared minus b squared minus 4ac v squared equals L. If you graph it in the plane, you get a parabola. And you get a hyperbola. And if b squared minus 4ac is negative, when you graph this equation in the plane, you get an ellipse. So this is the origin of the classification of second order linear PDEs. Let's go back. Here's the second order linear partial differential equation. We call this equation, let me give it a little name, I'll call it star. The PDE star is parabolic if b squared minus 4ac is 0. It's hyperbolic if b squared minus 4ac is positive, and it's elliptic if b squared minus 4ac is negative. So when we have a second order linear partial differential equation, such equations are divided into three classes. They're called parabolic, hyperbolic, or elliptic, depending on the value of the what is called the discriminant b squared minus 4ac. Just like you learned in high school, right? If you have a quadratic equation, b squared minus 4ac is the discriminant. If the discriminant is 0, your quadratic equation has one real root. If the discriminant is positive, your quadratic equation has two real roots. If the discriminant is negative, your quadratic has no real roots, but it has two complex roots. So, and in partial differential equations, the behavior is very different for these three categories of equations: parabolic, hyperbolic, and elliptic. Okay. So that's where we are. What's an example of a parabolic PDE? It's what they're there is something which is called the heat equation. So you have a function u is a function of two variables, x and t. So we think of this function, it has a certain value at a place x at a time t. It's a function of two variables. And the heat equation says that the second partial derivative with respect to x is some constant times the partial derivative with respect to t. Actually, let me write it the way the text does. It doesn't matter very much, but u sub t, the partial of u with respect to c, is some constant times the second partial of u with respect to x, and the constant is positive. So every positive number is the square of something. So the book writes it like this. Now, so this is the heat equation in one spatial dimension x. All right. We're going to spend a fair amount of time at the beginning looking at this particular equation. What kind of equation is it? Is it hyperbolic, elliptic, or parabolic? Can anyone tell me?
It's a parabolic, right?
Exactly, it's parabolic because if I rewrite it in the standard form, alpha squared uxx minus u sub t equals 0. If you think of the standard form a uxx plus b uxy plus c uyy, a is equal to alpha squared, b and c are 0. So b squared minus 4ac is 0. 0 and 0. So this is parabolic. So this, what is called the one-dimensional heat equation, is an example of a parabolic PDE. Now, let's look at this. So one of the interesting things about this subject is it arises in trying to understand nature, science, the world. And when you're looking at various physical phenomena, for whatever reason, it turns out that they often can be described by some kind of partial differential equation. And that is the example that we have here, starting in lesson 2 in the textbook. So this is a simple heat flow experiment. So we have a rod, a metal rod. And of some length, 0 to L. And we start out, so with this is a metal rod of length L, and the ends aren't covered, but the rod is insulated, except at the ends. So no heat can flow in or out of this rod except at the ends of the rod. is if you like, you wrap the rod in something, so no heat can go in or out, except at the ends. And we put this rod in an environment where the temperature is fixed. So the environment that we start with has a fixed temperature. Of T0 degrees centigrade. What is the standard unit for measuring heat? Someone tell me? It's the calorie. So when you measure heat, you're determining the quantity of heat is a calorie. Okay. So we put this rod in an environment of T0 degrees, and eventually the rod has this temperature everywhere, no matter where you measure the temperature, right? There's a nice picture in the book. You can imagine you have thermocouples, something that measures the temperature. And you can measure the temperature at any point on the rod that you like. And it's at T0 degrees. So now we take it out of this environment where the temperature is T0, and we apply heating elements to the ends. So we attach heating elements. So remove the rod from this fixed temperature environment, attach heating elements to the ends. So the left end has temperature T1 degrees. The right end has a temperature T2 degrees. So the book says, for example, if you want to make it concrete, suppose that originally the temperature of the environment was fixed at 10 degrees centigrade. And the right end is cooled to a temperature of 0 degrees. The left end, sorry. And the right end is heated to a temperature of 50 degrees. All right. So we have a very simple picture. We have a rod. The temperature, and the rod is metal rod. It conducts heat nicely. The temperature, the whole rod is a temperature when we start at T0 degrees. So U of xt is the temperature at position X on the rod. X is something between 0 and L at time T. So we have an initial condition. The initial condition at time 0 is that no matter where you measure on the rod, the position at X at time 0 is 10 degrees. So this is the initial condition. What is the boundary of this? What are the boundaries of this rod, the two ends? We have a boundary condition in addition to the initial condition. The boundary condition is that at the right end, U of 0t is 0 degrees for all time t greater than 0, right? You cool this to temperature 0. And at the right end, when x is equal to L at time t, this is 50 degrees for time t greater than 0. And we want to know, how does the temperature in this rod evolve with time? Right? So you have to understand the physical picture, because this is very beautiful and very simple. You have a rod, it's a metal rod at 10 degrees everywhere in the rod. And then, so the initial temperature distribution is at time 0, u of x comma 0 is equal to 10. But then you have a boundary condition. You're going to keep the left end at temperature 0, the right end at temperature 50, and the question is, what is going to happen to the rod? Are there any questions about this? This is a very simple physical picture. Right? Any questions? Well, I mean, what does the picture look like? Suppose you want to plot so here is x. What is the temperature? So at 10 degrees, this is the graph of u of x comma 0. For t greater than 0, the temperature at the left end is 0. The temperature at the right end is 50. So what do you expect to happen? If this is 0, as soon as you go in a little bit from the left end, you expect this to cool. If this end is at 50, and you start at 10, with time, you expect this part of the rod to heat up. So you might expect this rod, after a certain amount of time, to have a temperature distribution, maybe that looks like this. And after a little bit longer, maybe it looks like this. And what you might think would happen is, after a very long time, your temperature distribution simply approximates or gets closer and closer to the straight line between these 2 points. So this might be u of xt for some small value of t, but these time profiles approach this linear distribution of heat. So this would be the steady state. That should be what you approach. Now, using just the principle of conservation of heat, we will, not today, derive an equation that describes the evolution of the temperature distribution in this metal rod. And we get a certain PDE, which is called the heat equation, which says that the rate of change of the temperature, this is u sub t, partial of u with respect to t, at x as a function of x and t. This is the rate of change of the temperature, is some positive constant times the second derivative of x. The second derivative of x, for any time t, this is what? What does the second derivative tell you? Well, it tells you what is the convexity of the function u of xt at time t, right? So you have to remember calculus. This is actually first semester Calc 1. If you have a function u of x, the first derivative measures the rate of change. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. The second derivative measures the concavity. Concavity and convexity are the same thing. The function is concave up or convex if the second derivative is positive. It's concave down or convex down if the second derivative is negative. Are there any questions about that?
Yeah, is the rate of change of expansion?
Sorry?
You wrote the rate of change of expansion
Of temperature.
at temperature.
Yeah. Right? Because u of xt, this is the function which is the temperature in the rod at position x. The rod is of length L, x is between 0 and L, at time t, t greater than or equal to 0. You start with the rod at the fixed temperature everywhere at 10 degrees, it's constant. Then you set the left-hand boundary to be 0 and the right-hand boundary of the rod to be 50 degrees. And you look at how the temperature changes in the rod. So u of xt is the temperature at time t at position x. So if you fix t and you plot u of x, that's what I've done here, for a certain value of t, let's say, a minute after you start, the temperature will be 0, start to increase, and end up at 50. So here the rod is cooling, here the rod is heating. And for a fixed t, the second partial derivative measures convexity. So let's recall, uxx greater than 0 implies convex up. What does convex up mean? Well, it means if you look at the, so here I have a value x. And suppose I go a little bit to the right, x plus delta x, and a little bit to the left, x minus delta x. And I'm going to graph, this is for fixed t. U of xt, if it's convex up, it looks like that. Convex up. Here is the value of the function at ux minus delta x. Here's the value of the function at x plus delta x. What does it mean to be convex up? It means the graph lies beneath the chord. So convex up means the value of the function at x at this time t is less than this value. What is this value? This is the midpoint of the values here and here, the average rather. This is u of x plus delta x plus u of x minus delta x over 2. If I take the average value of u at these 2 points, that's what this is, comma t. So to say the function is convex up means that the graph of the function lies below the chord on any 2 points on the curve in that region where it's convex up. So this is u of x. this point here is the average of this and this. So this is Calc 1, first semester freshman calculus. This is what convexity means. Are there any questions about this?
Yeah, about the graph, when the heat is slowing down, what is the graph represent? The cup.
I'm sorry, I didn't hear what you said. Would you repeat it again a little bit more loud?
Yes, I'm talking about the graph.
This
that
one
you,
here at the top?
right. When the heat is down,
What do you mean by down?
down, it's slowing down. You know, the heat is slowing down.
Well, I'm not sure what you mean by slowing. So this is not anything changing with time. So for example, this would be the heat distribution in the rod at some time, T. If you start, it's all at temperature 10 degrees. But if this end is fixed at 0, the temperature here is going to drop. Here, if the temperature is set at 50, close to that end, the temperature is going to increase. It's going to heat up.
Oh, okay.
So this is not the result of an experiment. This is just a rough picture of what will be happening. That is, at any given time, a little bit after you start, this part of the rod is cooling, this part of the rod is heating, and you'll have a distribution of temperature which looks something like that. When you analyze, so we haven't solved the heat equation. When we solve the heat equation, we should see that we get a solution at every time t, and as t goes to infinity, as time marches on, the heat distribution should approach this straight line, which is a steady state solution. That's what we would expect to see. For this parabolic equation, we would expect to see some limit. But what I want to do is just give some motivation for what's going on, just physically what you expect. So what this says is that if you have a rod, or this is what you should expect, if you have a rod and the temperature at some point, x, is less than the temperature at 2 nearby points, or the average of the temperature at 2 nearby points, what would you expect will happen? So, I mean, just think of it. Here's your rod. Let's say, maybe here, this is the temperature is at 20 degrees. And maybe this is 10 degrees and this is 100 degrees. The average of these two is what? 55 degrees. We would expect this temperature to increase. So we would expect that if the temperature at some point is less than the average of the temperatures at 2 nearby points, then the partial view with respect to t should increase. We expect the temperature to go up. The rate of change of temperature at that place should increase. And if this were negative, if the temperature at this point were less than the average, were greater than the average, I mean, suppose this was 120 degrees, we would expect the temperature here to cool. Again, if you look at the book, the pictures are very, well, they're well drawn, obviously, because it's a book. So from the text, here's our rod of length L. This is the left end, this is the right end. This left end is fixed at a temperature T1. The right end is fixed at a temperature T2. At time 0, the rod has a constant temperature T0 everywhere. So this is a graph of temperature. This is temperature profiles at different times t. At time 0, the graph's a horizontal line. But what happens with time as time increases? This part will cool, this part will heat. And we expect the limit probably to be just this linear distribution of temperature from the low left end to the high right end. Suppose at some time, this is a graph of the temperature. And here's a certain point x at time t. Well, it's like, yeah, well, and here, this curve is convex down. The second derivative is negative, it's convex down. And if you look at the average of the temperatures at endpoints of this interval, it's below the curve. So the temperature at time t is greater than the average of the temperatures at these nearby places. So we expect in that case, the temperature to decrease. We expect cooling. So if the second derivative is negative, if uxx is negative, we expect the partial of u with respect to t to be negative. Here's a different part of the curve. Here, the curve is convex up. Here, at any point, the value of the temperature is less than the temperature of neighboring points. So we expect the temperature to increase. So where the second derivative is positive, and the curve is convex up, we would expect that temperature will increase, so the partial of u with respect to t will increase. Right? So the minimum we would expect is that the partial of u with respect to t has the same sign, positive or negative, as the second derivative. Let's see. That is exactly what the heat equation says. The heat equation says it in a much more precise and strong fashion. It says that this is a positive number. So if the curve is convex up, this is positive. This is positive. That means the rate of change of u is positive. It's getting hotter. The temperature is increasing. If the curve is convex down, this is negative. Partial of u with respect to t is negative, so the rod is cooling. That's the information we get. Well, that's the information we get. Let me just summarize one part of this and to have things clear in our heads. So first of all, we have the heat equation. Then we have the initial condition that u at time 0 has some value. In this case, it was 10 degrees centigrade. Then we had boundary conditions. We had boundary values. That at the right-hand endpoint, at the left-hand endpoint, x equals 0, at every time we had a temperature of 0. At the left-hand endpoint, when x is equal to L, we have a temperature of 50 degrees. So when you put all this together, you have IBVP. This means this is an initial, I is initial, boundary value problem. Initial boundary value problem. So the typical problem in partial differential equations is given a partial differential equation. Here's a partial differential equation and some initial condition and some boundary values. Find a function u that satisfies the equation and the initial condition and the boundary values. It could be there's no solution. It could be there's exactly one solution. It could be there are 2 or 3 or 4 solutions. It could be there are infinitely many solutions. All of that depends on the problem. But the standard thing we deal with in partial differential equations are things which have this abbreviation, IBVP, initial boundary value problems. And that's exactly what we saw here for heating the rod. We have the heat equation. This is this partial differential equation. It's an equation of 2 variables, position x and time t. It has an initial condition at time 0, and it has boundary conditions for all time. In this case, these initial and boundary values are constants, but they could vary. That's not necessarily, it depends on the problem.
Professor, ordinary differential equations in the real world like partial, is very related to this example, right? In just one variable, because we are looking for more than one variable in our class. Ordinary differential equations, they have examples similar to the heating rule or different sample they use.
Well, so if you're looking at heating of something, what you're usually interested in is what is the temperature at a certain place. So you automatically have 2 variables. You have the temperature, you have the time, and you have the place. So, I'm going to talk a little bit about ordinary differential equations, but this problem is a problem that involves 2 variables, time and place, t and x. Right? And the homework that's due on Wednesday is the homework from lessons 1 and 2 of the book. This is the text. And I'll go over some of them on Wednesday. And the instructions about how to turn in the homework on the internet are you already have. Okay? Now, there's a little bit of ordinary differential equations that you learn in Calc 2, but very often the way you solve a partial differential equation is to reduce it to an ordinary differential equation. So if you can't solve the ODE, you won't be able to solve the PDE. And I'm going to spend a little bit of time this week talking about ordinary differential equations. And I already copied and sent to you, as well as posted on the website, some information, a text about, maybe 10 pages or so on ordinary differential equations. And I'm going to go through that, and we'll have some homework for next week involving ODEs, because again, you can't solve a PDE if you are unable to solve an ODE. So What is the simplest kind of ordinary differential equation? You have some unknown function u or f or y, and we're told that dy dx is some function that only depends on x. Find y. And, well, this is just calc 1, because if dy dx is f of x, that means y is the antiderivative. Well, maybe I shouldn't, I'm not going to call this f of x. I'm going to call it p of x. Means y is the integral of p of x dx, any derivative plus a constant. That's all it is, right? I mean, that's the first thing you learn in calculus. So if you had the differential equation dy dx equals sine x, what is the solution? Y is the integral of sine x plus c, dx. So it's minus cosine x plus a constant. Right? So that's the solution. That's all there is to it. What's the next simplest? Well, you might have a problem where you want to find, let's say, dy dx is equal to some constant times y. Right, this is k times y. And you know that one solution is y equals c e to the kx, again, for any constant c. Here also. Right? So if you have this differential equation in one variable, y is a function of x, if dy dx is k times y, there may be more solutions, but you know at least one solution. Y is c e to the kx, and you can check by differentiating. Okay. Any questions about that? Is that okay? All right. Now, the first class of equations you consider in ordinary differential equations is a first order linear ordinary differential equation. So if the unknown function is y, this would have the form dy dx. I'm going to make it really simple, where the coefficient of dy dx is just 1, plus p of x times y equals q of x. So this is first order. First order means the highest derivative is a first derivative. There's no second or third or higher derivatives. So the first derivative plus some p of x, some function of x times y is q of x. And to make it even simpler, we consider the homogeneous equation. That means the right-hand side is 0. So the homogeneous equation is just dy dx equals p of x times y. Sorry, plus p of x times y equals 0. Okay. Any questions about that? Well, let's solve the equation. Suppose, just to make it a little bit easier, p of x is greater than 0 for all x in some region. So if we have dy dx plus p of x times y equals 0, I can write that as dy dx equals minus p of x times y. Or 1 over y dy dx is minus p of x. So I'm just taking my homogeneous linear first order differential equation, writing it like this. And 1 over y dy dx, if y is positive, this is just the log of the derivative of the log of y. By the chain rule, the derivative of the log of y is 1 over y dy dx. So that's equal to minus p of x, which means if I take the antiderivative, the log of y is the integral of minus p of x dx. Plus a constant. I'm just going to write this as minus the integral of p of x minus c. And I'm going to call this a of x just for brevity. So if I exponentiate, y is equal to e to the minus a of x. So I've solved the problem. And you can check by differentiating dy dx. If I differentiate this by the chain rule, this is the derivative of minus a of x times e to the minus a of x. This is a of x. If I differentiate, I get the derivative of the integral is minus p of x, e to the minus a of x, which is minus p of x times y. So dy dx plus p of x times y is 0. So for every constant c, this is the solution of the differential equation. Let's do a simple example. Suppose I had the equation dy dx plus cosine x times y equals 0. So p of x is cosine x. The integral of p of x is the integral of cosine x, is sine x plus a constant. So a of x is minus sine x minus c. So the solution, a of x, is minus, not minus, is sine x plus c. So my solution is y equals e to the minus a of x. That's e to the minus sine x minus c, or some constant c1, e to the minus c1, e to the minus sine x. And you can check by differentiating that, in fact, that's the solution. Sorry, so what I encourage you to do is to look at the notes that I distributed yesterday or last night, I think, on ordinary differential equations. Of course, we're going to talk about that a lot on Wednesday. And for next week, there will be some homework solving some of the problems that were on that handout. But this is, there's not a lot of ordinary differential equations we're going to need in dealing with PDEs, but there is some. And since ODE is not a prerequisite for PDE and for this course, we're just going to prove some of the simplest theorems about ordinary differential equations. Right. Are there any questions? Okay, if not, we're going to end. This lecture will be posted on YouTube very soon. And if there are other questions, at 1 o'clock, I have an office hour, and you're welcome to log on. The log on information, the Zoom information for the office hour is on our Blackboard website. And otherwise, we meet again on Wednesday at 11. Next Monday, a week from today, is Labor Day, so there's no class next Monday. All right, well, if you don't have the book, what I will do today is I will scan the homework problems and I will distribute them. So if you don't have the book yet, you'll have the homework problem sometime later this afternoon. I'll make sure I do that. Okay. All right, if there's nothing else, I will say goodbye to you all.